Hi everyone. Um, so far we have seen about classical free electron theory, derivations of electrical conductivity, thermal conductivity, Wiedemann-Franz law, and also seen about some band structures, energy levels, shells, etc. Now in this video, I'm going to show you the Fermi-Dirac statistics. Okay, uh, Fermi-Dirac statistics deals with electrons of spin, the electrons of spin half. Okay, spin half. This is deals with fermions. Fermions are particles which have half spin. So electrons are having half spin. So Fermi-Dirac statistics deals with fermions, lies electrons, which is having half spin, and this electrons will obey Fermi-Dirac statistics. I will tell you what is Fermi-Dirac statistics. Before that, we will see what is Fermi-Dirac statistics. Okay, this tell you the distribution of electrons in various energy levels in mathematical form. Okay, so in last slide we have seen the band structure and distribution of electrons in K shell, L shell, M shell. Okay, so the mathematical formula for that distribution is this one: f of E is equal to 1 by 1 plus E minus EF divided by KT. Okay, so this Fermi-Dirac statistics will tell you the distribution of electrons in various energy level. Now see here in metal, valence band, conduction bands overlap with each other, and see in valence band, uh, up to this level the electrons are filled. So this level is the maximum level. So this level is the Fermi energy level. So maximum energy level, the electrons fill at 0 Kelvin. So that is known as Fermi energy level. So this this is the distribution of electrons from this is how the electrons distributed throughout the energy level. So Fermi energy level will tell you the distribution of electrons in all energy levels in the mathematical form. So in metal, valence band, conduction band overlap with each other, and the maximum level is this, up to which the electrons will occupy, and above this there is no occupation of electrons. All the levels are empty. Below of Fermi energy level, all the levels are occupied. Above the Fermi energy level, all the levels are empty, and the maximum energy level up to which electrons occupied are known as Fermi energy level. Okay, this is, if you consider metal, this is a form of band structure: valence band, conduction band. And if you consider a semiconductor, you're seeing that Fermi energy level is in between the valence band and conduction band. Okay, so usually will represent like this: Fermi level is in between the valence band and conduction band. So keep it in mind, Fermi energy level will give you the distribution of electrons in an among various energy level. This is the mathematical form: f of E is equal to 1 by 1 plus e power E minus EF divided by KT. E is the total energy, EF is the maximum level of occupied energy, that is Fermi energy level, K is the Boltzmann constant, T is the temperature. So this is the mathematical form for the distribution of energy level, and this is known as Fermi-Dirac statistics. If f of E is equal to 1, we can say energy levels are occupied by electrons. If f of E is equal to 1, we can say that energy levels are occupied by electrons. If f of E is equal to 0, we can say that it's a vacant energy level. There is no occupation of electrons, so it is vacant energy level. If f of E is equal to 0.5, we can say 50% of electrons are occupied by the energy level. Okay, so by using this, we can say the distribution. If f of E is equal to 1, all the electrons are distributed. F of E is equal to 0, no electrons are distributed, it is 0, we can have a vacant energy level. If f of E is equal to 0.5, 50% of electrons are distributed in the energy level. So Fermi-Dirac statistics or Fermi-Dirac function is a very important functions which tell you the distribution of electrons in the various energy level, probability of distribution of electrons. Okay, so when we talk about metals and when we talk about semiconductors, this Fermi energy levels very important. Always it will talk about the distribution of electrons. If you consider semiconductors, Fermi energy level will change according to the adding of impurities. That we will discuss in the later classes while discussing semiconductors. So if you consider semiconductor, Fermi energy level will arise up or it will come down according to the impurity you're going to add. So in metals, this is the formula. In metals, it is here the Fermi energy level is here. We are not going to add any dopant in metal. So, but in semiconductors, we are going to add some impurities. So there will be some changes in the Fermi energy level. So Fermi redox statistics will tell you about the probability distribution of electrons in the energy levels. Thank you.